Hello everyone, welcome to this tutorial. I'm John Alway. In this video, I will present details of the decoder transformer. The decoder transformer is a large language model artificial neural network. This includes such popular examples as ChatGPT, Grok, and Gemini. The AI revolution has been here for a few years, and I want to relate to you what I've learned in my study of the technology. From this tutorial, you will gain a big picture understanding of the decoder transformer, and then you will learn about the mechanical details. I will go through each major component in a flow chart diagram. I'll also discuss a bit on how it is able to understand language and meaning, how it is able to convey real meaning as if it were an intelligent agent. Okay, and here are the things, the bullet points here. This is a decoder transformer. The purpose is to provide a big picture overview. This is a large language model, LLM. It's an artificial neural network. Examples are ChatGPT and Grok, and Gemini, as I mentioned. To provide a big picture, I'll give a brief description of each major component in the model. And that's the big thing right here. I'm giving a description of each major component in the model. The decoder transformer has two modes of operation, training and inference. Training is when developers feed masses of text data into the decoder transformer models so that they learn the text. And this often takes weeks and months. Inference mode is when a user uses a trained model, such as ChatGPT. This tutorial will focus on inference mode. A future tutorial will focus on training. I also want to make the point that this tutorial is broken up into three videos, three parts. Part one, this part, is the introduction, and the first will be the introduction and discuss the first few components of the pipeline. Part two will be on the self-attention mechanism, the technological breakthrough behind the LLMs. Part three will be the rest of the pipeline and a word on the decoder transformer, on how the decoder transformer is able to output meaningful text. Note, you cannot skip parts. All parts are necessary to understand the material. So you have to go in order to understand the material here. Okay, I thought I'd relate some general points about decoder transformers, especially the large language models such as ChatGPT. In this video, I want to discuss the nuts and bolts of the flow logic of a decoder transformer, but I thought it would be worthwhile looking at other aspects that are required to implement the model so that you can better understand the scope of these models. And here you see some points. Because these are data-driven models. They are programmed by being trained on millions of documents of text. In traditional programming, programmers write lines of code that execute specific functions. They're very controlled. For these LLMs, all artificial neural networks, the models are trained on lots of data before they can be used. So it's less controlled. Yeah, they have to feed a lot of data in there to try to get things to learn properly. The commercial LLMs such as ChatGPT are superclusters. Basically, these are large-scale distributed systems made of thousands of interconnected servers. Each server contains multiple GPUs, graphical processing units. They are designed to support training of massive neural networks. The GPUs are specialized for the task of operating on tensors, that is matrices and vectors that make up an LLM. And there can be 10 billion to up to a trillion parameters for weights and biases of some of the models. They're trained on hundreds of gigabytes of input data. It takes weeks to months to train. And of course, when they're serving users, it requires thousands of GPUs to serve millions of users once it's in inference mode. But training mode requires more intensive computational power. Okay, the next thing is here's a flow chart, a 30,000-foot aerial view of the decoder transformer in inference mode right here. This gives you a powerful way to conceptualize what the model does without knowing the details. In a nutshell, what it does is it takes input text and processes it to predict the next word. That's the essence of what it does. That's really all it does, is predict words, predicts the next word. The idea of predicting the next element from a sequence of prior elements is referred to as autoregression. So this is an autoregressive model. It will predict the next word, append that word. So it predicts the next word, appends that word to the input text, and feeds that in to predict yet the next word. And when it predicts that word, it'll append that word onto the text, feed all of that text sequence in, and predict yet the next word. Continues on and so on to output its response to any input you might put in there, like how do helicopters fly, or what is the answer to life, the universe, and everything. You might put that in as your input, right? And it will predict the next word and over again. And the only thing that stops it is it also is trained for end of sequences. So an end of sequence token pops up and it ends the process. That's how it works. An important paper was published in 2017 called "Attention is All You Need," and it was authored by several engineers at Google, and is the original paper that defined how modern LLMs work. The paper introduced the encoder-decoder transformer model. Notice it's encoder-decoder, not just decoder. This paper holds the innovation that launched LLMs into public awareness. So it's very important. It's a seminal paper. As I mentioned, that has the encoder-decoder. We're on decoder only, so we're only using part of the design. But we're doing this because ChatGPT and Grok are decoder only. They operate that way, so that's really, why I'm looking at that. Also, if you cover decoder, it's very similar to the encoder. So when you cover one, you're covering most of the other one as well. There will be aware that there's a lot of there's math discussed in this video. The decoder transformer is all based on math. It uses matrices, vectors, dot products, activation functions, etc. If you really want to know what's going on, it's good to know these things. Okay, now for the components flowchart. This is going to be the map we're going to follow. This is a flowchart, a pipeline of the decoder transformer's main components in inference mode. I will go through each of these components and use this flowchart as a guide through the tutorial to show the way. To be clear, this is not much different there's not much difference in the components in the inference mode versus training mode. The only block not in the training mode here is the randomized selection block at the end of the flowchart. Everything else is in harmony with the training components. This This flow chart gives you a big picture map of the logical flow of a decoder transformer. So that you can picture it, and it will tell you where we are in this tutorial. Okay, let's look at each very briefly. I'll go over each, and then we'll in the slides coming up, I'll discuss each in more detail. Okay, this is the input text and tokenizer. The input text is turned into tokens by the tokenizer. The tokens are stand-ins for words. The dictionary holds the set of all tokens that the decoder transformer handles. The tokens are represented by high-dimensional numerical vectors. So the word sequence is turned into a token sequence, which is then turned into a sequence of vectors. So you get tokens. The tokens are mapped to vectors, and the vectors, so you end up with a sequence of vectors from a sequence of words to tokens to vectors. And because computers love math, so it's numerical vectors, high-dimensional numerical vectors. And then positional encoding. Each vector is encoded with a position. For example, for the sentence, "The cat sat on a mat," the first word is "the." Cat is the second word, and so on. This is required. It's required that you know that you do this, that you provide a positional encoding, because it's not a sequential network. It doesn't know word order, so you have to give it a pattern so it recognizes it. It's a parallel. The decoder transformer operates in parallel. It processes data in parallel. All of the input tokens are processed in parallel operations. So that's why you have to have positional encoding. Then here's the heart and soul of it. The transformer blocks. You can see down here, transformer block. The transformer block has two main components. The self-attention mechanism. This is the big deal right here. And the feed-forward network. This is the innovative genius of the decoder transformer, the self-attention mechanism. So I'll be doing this in the next video, covering this in the next video, in this part 2 of this tutorial. This is the feed-forward network, a fully connected neural network. These two components are vital for the decoder transformer. And notice I've got more than one of these. I got 1 to n, and n means a model can have any. You can have any number in a model. For example, ChatGPT 1 of them has 96 of these, one after the other in series. One feeds into the other, 96. And this is a way that, this is really the heart and soul of the decoder transformer. This is all the setup, and this is the heart and soul of it right here. And these are doing the major processing. Okay, and then this is the output part. And then this builds up knowledge layer by layer. It becomes more and more abstract. Then you get to the final linear layer. This is where the final value is predicted. The word is predicted, okay? And it gives a set of raw scores called logits. And the highest score is the best selection, but randomization is often thrown in. So it won't always take the highest score. It'll often take scores that are close to the highest by randomizing it. This makes the model more interesting and less predictable. And then you end up with a predicted word at the end there, and there you have it. That's what it does. And that's tacked on to the input text and fed through again, as I mentioned earlier, until there's an end of sequence token predicted. So that's the big component overview flowchart that we're going to be following. Okay, now the next part. Okay, these two elements, these two components. How input text is tokenized and the context window. This is the important setup for the rest of the pipeline. So it's important for the setup. The first thing to look at is the input text. This usually starts with a question entered by a user, such as, what is the airspeed velocity of an unladen swallow? You might recognize that one. So you put that in there. Typically, byte pair encoding is used to tokenize words. So usually that's a method used, is byte pair encoding to tokenize. And in this case, the tokenizer takes words and either keeps them as a complete word or breaks them down into words, and either breaks them down into common subwords or will even break them down into characters if necessary. And you see an example here is unbelievable might be broken up like this as an example. And it's just an example. It could be anything, you know. And okay, and there are three advantages to using a byte pair encoding to tokenize. Where a tokenizing is, it keeps the dictionary size manageable because you can use combinations of tokens to create words. So pre-existing components can be tokens can be made to create words. It solves the out-of-dictionary problem, which happens when a word you come across is not in the dictionary. If you don't use tokenizing, it will halt the system because it won't know what to do with a word it just doesn't know. But this solves that problem. It also effectively handles misspellings. So, you know, those are some real values it has. So when a sentence is input into the decoder transformer, it is converted into a sequence of tokens by the tokenizer. The tokens will fill a context window, which is the upper limit to the number of tokens the decoder transformer can handle in any one pass. A real world example is GPT-3, which has a context window size of 2,048 tokens. Okay, the next thing is the dictionary, also known as the embeddings matrix. It holds all of the meanings for the tokens known by the decoder transformer. These act as the building blocks used by the decoder transformer. The embeddings are high-dimensional numerical vectors that define the tokens or words. These are large vectors. There are some wild things about how this works. Word meanings can actually be established in a high-dimensional vector space. The meanings are established by placing words in the right positions with respect to other words in the space. So the relative position of word vectors is key to meaning. The more words you add to the system, including the same words in lots of varied contexts, the more refined the meanings become. So that's an important big picture idea there. The dictionary holds a high-dimensional vector for each and every token defined in the model. These vectors define the words in a high-dimensional numerical space. To give you an idea of how large they can be, ChatGPT-3 has vectors with 12,288 dimensions. That's how big the dimensional space is. You you know, imagine X, Y, Z, that's just 3 dimensions. This has got 12,288, and it has that many dimensions to define a word. And each dimension might be a feature in of a word, you know. Okay, after the input text is tokenized, the dictionary is used to convert all of the tokens into vectors. Okay, into their particular vectors, because every token has its own unique vector. So you end up with a sequence of vectors. So you go from input text to tokens to vectors, a sequence of vectors. And this is the result is that the input text is converted into a sequence of vectors. So what were a sequence of words now become a sequence of numbers. Computers do better with math, you know. So they're going to use math to do the calculations and to understand the text. The dictionary is created and trained. This dictionary is created and trained before the model itself is trained. This means that the set of words or tokens is established before training the model itself. So in effect, the set of tokens in this dictionary, which has a set of tokens mapped to vectors by the dictionary, in the dictionary. Okay, what I mean, the set of tokens is fixed and set at the start in inference mode. So that's fixed. That whatever that thing is defined as is fixed for inference mode. All the vectors are fixed. During training mode, they are trained to be certain values, but in inference mode, they are fixed at those values and they never change. These are the set of tokens are like the building blocks for the decoder transformer uses to build knowledge. Everything is built out of these blocks, out of this fixed set of blocks. All knowledge is built from those blocks. That's the input data, and it's all in terms of those tokens, and which means those vectors. To give you an idea of dictionary size, GPT-3 has about 50,000 tokens in its dictionary. So it's sort of large, but not really super large. You know, it's very manageable. In this tutorial, I'll refer to input text in embedding vector form as an input sequence, an embedding sequence, and sometimes as just an input vector sequence. Or yeah, so that's yeah, okay. Okay, we've learned that words are represented as vectors, and now we learn that you can do meaningful math with those vectors. The fact that this is true makes me wonder how effectively mathematics for human language could be developed. There may be some magic in there. But here's what I'm referring to. We know that words or tokens in the model are represented by vectors. It has been found by observation that after having been trained, the vectors have a semantic logic to them. For example, the math here. Look at the math here. And this makes semantic sense. You can if Q is for queen, Q is a vector for queen, K is a vector for king, and M is a vector for man, and W is a vector for woman. This sort of equation actually works, it's been found. You can say king minus man plus woman is equal to queen. That actually works, and it's found for case after case of different vectors, different words, different tokens, that this is true, that this actually works. So that's a pretty remarkable thing to keep in mind. It's worth noting, and it's worth understanding. Okay, we know that we have now have a sequence of words turned into a sequence of vectors, and that's going to go. The next step is positional encoding. Because the decoder processes its entire context window in parallel, it has no way of knowing the position of words in the input sequence. It is vital that the model be aware of the word position, because position is often important to meaning, so that information has to be added. It has to be aware of that. So they had to figure out a way to do that. One thing about these deep learning models is that they can often figure things out on their own if you provide the information to them in the right format. And that's what they did here. In order to overcome this problem, the creators of the decoder transformer decided to stamp each token with a unique pattern according to its position in the sequence, in the sentence, in the word sentence, or sentences. It provides the actual position, like position 1, position 2 for each word, and then a sentence. They do it by giving each token a pattern according to the position it holds in the sentence. And position 1 always has the same pattern. Position 2 always has the same pattern. And with this means that they put the pattern in there, and this means that the neural network can figure out position by going through, by being trained on millions of examples. So millions of examples, it figures out, hey, that means that. It will recognize the patterns that are in there. A common algorithm used for this is the sine-cosine algorithm right here. I mentioned here, and this pattern doesn't overwhelm the existing data and isn't too small to be pulled out. So it can it's not so big that it overwhelms the signal there, not so small it can't be the artificial neural network doesn't notice it. It'll notice it. The sine-cosine version is clever because it helps the model understand both absolute position and relative distances. I will also note that positional encoding gives the model the power of determining permutations instead of just combinations. That is, it can recognize different word orders. For example, it can recognize the difference between ABC, BAC, CBA, etc. So that's a power it has, and that gives it a lot of power, and that's important for grammar and things like that. So it's a powerful tool in its arsenal. Okay, that's it for this part of the tutorial. The next thing we'll discuss in the part 2 is the self-attention mechanism, which is really the heart and soul of a decoder transformer. And it's kind of a more difficult to understand this than what we've covered so far. So you're going to have to really buckle down for it. But it's really cool the way it works. So we'll get to that in the next tutorial. So I'll sign off for now and see you in the next video.